Let's understand matter. Everything is matter. Anything that takes up space is matter. Desk, paper, pencil, and even the air we breathe are matter. Everything that has mass and volume is called matter. Mass is the quantity of matter in an object. Volume is the amount of space matter takes up. Let's understand what is mass. Mass is the amount of matter in an object. Mass is constant. Mass is also the measure of inertia. Let's understand weight. The measure of the force of gravity on the mass of an object. Weight changes with gravity. Our weight is how heavy we are on this planet. Weight on the surface of Moon. The metric unit for weight is Newton, N. Let's understand the kinetic theory of matter. 1. All matter is made up of atoms and molecules that act as tiny particles. 2. These tiny particles are always in motion. State of matter depends on its molecular motion as measured by temperature. Increase in temperature is equal to increased motion of particle. Decrease in temperature is equal to decreased motion of particle. 3. At the same temperature, the heavier particles move slower than the lighter particles. Let's understand temperature. A measure of the average kinetic energy Ke in a sample. Temperature at which all molecular particle motion stops. 0 Kelvin, minus 273 degrees Celsius, minus 459 degrees Fahrenheit. Let's understand intermolecular forces, IFs. Force of attraction between molecules or particles. Becomes stronger as molecules get closer together. Therefore, IFs are strongest in solids. Let's understand classification of matter. Matter can be classified by its state. Matter is made up of particles. These particles have characteristics specific to each of the individual states of matter. The 3 states of matter are solids, liquids, and gases. Let's look at the arrangement of particles in different states of matter. Solids. In a solid, particles have less energy, are tightly packed together, dense, as the intermolecular force of attraction for solid matter is very strong. As a result, these solid particles do not move very much. Solids have a definite shape and volume. Liquids. In a liquid, particles have more energy, are less tightly packed, less dense, as the intermolecular force of attraction for liquid matter is weaker than solid matter. These liquid particles can move freely. Liquids have definite volume but no definite shape. Instead, they take on the shape of the container. Gases. The particles in a gas have the most energy and are free to move around and so spread out rapidly. Gases do not have a definite shape or volume and expand to fill the entire container. Let's understand solid. Every solid has a definite shape and a definite volume. Solids have weight. Solids take up space. The molecules in a solid are held very close together. Kinetic molecular theory. Molecules are held close together and there is very little movement between them. Let's understand liquid. A liquid does not have a definite shape but does have a definite volume. Liquids have weight. Liquids take up space. The molecules in a liquid are not held as closely together, so they can slide past each other. Kinetic molecular theory. Atoms and molecules have more space between them than a solid does, but less than a gas, that is, it is more fluid. Let's understand gas. Gases don't have a definite shape or volume. They expand or contract to fill the space available to them. Gases have weight. The molecules in a gas are spread very far apart and can move in any direction. Kinetic molecular theory. Molecules are moving in random patterns with varying amounts of distance between the particles. Solid plus energy is equal to what? When energy is added to solids, they become liquids. Solid plus energy is equal to liquid. Liquid plus energy is equal to what? When energy is added to liquids, they become gases. Liquid plus energy is equal to gas. Gases have very high compressibility. They can be compressed into a very small volume by applying pressures. Due to its high compressibility, fairly large mass of a gas can be put in a small cylinder by compression. The cooking gas that we use in our homes is a compressed gas. Let's understand the effect of change of temperature on solids. On increasing the temperature of solids, the kinetic energy of particles increases. Due to the increase in kinetic energy, the particles start vibrating with greater speed. The energy supplied by heat overcomes the forces of attraction between the particles. The particles leave their fixed position and start moving more freely. A stage is reached when the solid melts and is converted to a liquid. Let's understand the effect of change of temperature on liquids. When we supply heat energy to water, particles start moving even faster. At a certain temperature, a point is reached when the particles have enough energy to break free from the forces of attraction of each other. At this temperature, the liquid starts changing into gas and finally gets converted into gas. Let's understand the effect of change of temperature on gases. When we supply heat energy to gases, the kinetic energy of particles increase and the particle motion increases and the particles move with a greater speed. Let's understand latent heat. Latent heat is the heat released or absorbed by a substance without any change in temperature. This happens when state of matter changes from one to another. Every substance has some forces of attraction between its particles which holds them together. Now, if a substance has to change its state, then it is necessary to break these forces of attraction between the particles. The latent heat which we supply is used up in overcoming these forces of attraction and so does not increase the kinetic energy of the particles and hence no rise in temperature is visible. For example, when solid ice melts into liquid water and when water boils to form vapor. Notice, in the experiment at 0 degrees Celsius, state changes from ice to water, but temperature does not change. Similarly, at 100 degrees Celsius, water changes to vapor and temperature remains unchanged. This explains the concept of latent, hidden heat required to change state, heat. The term was introduced around 1762 by Joseph Black. The word latent means hidden. This latent heat is hidden in the substance undergoing the change of state and does not show its presence by raising the temperature and hence cannot be detected by a thermometer. In contrast to latent heat, an energy is called a sensible energy or heat when it causes processes that do not result in a change of temperature of the substance. For water, the latent heat of fusion, heat needed to melt ice to water, is 79.7 calorie per gram. For water, the latent heat of vaporization, heat needed to boil water, is 540 calorie per gram. For alcohol, the latent heat of vaporization is 204 calorie per gram. Let's understand sublimation. Sublimation is the process of transformation directly from the solid phase to the gaseous phase without passing through an intermediate liquid phase. Solid carbon dioxide, dry ice, sublimes readily at atmospheric pressure at -78.5 degrees Celsius, 197.5 Kelvin, -104.2 degree Fahrenheit. Snow and ice sublime, although more slowly, below the melting point temperature. This allows a wet cloth to be hung outdoors in freezing weather and retrieved later in a dry state. Iodine produces fumes on gentle heating. Naphthalene, a common ingredient in mothballs, also sublimes easily. Ammonium chloride, when heated, undergoes sublimation. Let's understand what is temperature. Temperature is a physical property of matter that quantitatively expresses the common notions of hot and cold. Objects of low temperature are cold, while various degrees of higher temperatures are referred to as warm or hot. Quantitatively, temperature is measured with thermometers, which may be calibrated to a variety of temperature scales. The common used units of temperature are the following: Celsius, Kelvin, Fahrenheit. Kelvin K is the SI unit, but since it has the same size degree as Celsius, the two scales are used interchangeably for the appropriate ranges of temperature. Kelvin is equal to degree Celsius plus 273. K is used where the temperature is very low, example 40 Kelvin, or very high, example 2000 Kelvin, with Celsius used for everyday applications. 0 Kelvin is equal to minus 273.15 degrees centigrade. Kelvin uses the same interval as the centigrade Celsius scale. It was created with 0 at the lowest possible theoretical temperature, absolute 0. Kelvin is written without a degree sign and with an uppercase K. Example, the melting point of ice is 273.15 Kelvin. Let's understand what is pressure. Pressure is an effect which occurs when a force is applied on a surface. Pressure is the amount of force acting on a unit area. The symbol of pressure is P. Let's understand the changing states due to change in pressure. Changing states may also be due to the change in pressure in a system. Increase in pressure decreases the distance between the particles of a gas, allowing interparticular forces to become large enough to liquefy the substance. When a high pressure is applied to a gas, it gets compressed into a small volume, and the particles get so close that they start attracting each other sufficiently to form a liquid. When a gas is compressed too much, then heat is produced due to compression. So while applying pressure, it is necessary to cool them to take away the heat produced during compression. Cooling lowers the temperature of compressed gas and helps in liquefying it. Let's understand plasma. Lightning is a plasma. Used in fluorescent light bulbs and neon lights, plasma is a mixture of free electrons and ions. Plasma is a lot like a gas, but the particles are electrically charged. In an ordinary gas, each atom contains an equal number of positive and negative charges. The positive charges in the nucleus are surrounded by an equal number of negatively charged electrons, and each atom is electrically neutral. A gas becomes a plasma when the addition of heat or other energy causes a significant number of atoms to release some or all of their electrons. The remaining parts of those atoms are left with a positive charge, and the detached negative electrons are free to move about. Those atoms and the resulting electrically charged gas are said to be ionized. When enough atoms are ionized to significantly affect the electrical characteristics of the gas, it is a plasma. The sun and other stars glow because of the presence of plasma in them. Let's understand Bose-Einstein condensate. Bose-Einstein condensate is a state of matter in the sense that solid, liquid, gas and plasma are states of matter. Bose-Einstein condensates from matter that has been cooled to near absolute zero. Predicted in the 1920s by Satyendranath Bose and Albert Einstein based on Bose's work. Bose-Einstein condensates are extremely fragile. The slightest interaction with the outside world can be enough to warm them past the condensation threshold, causing them to break back down into individual atoms again. Let's understand evaporation. Evaporation is a process by which liquid water passes directly to the vapor phase. Liquid can change to vapor even at temperatures below the boiling point. Let's understand evaporation and particle motion. Evaporation is the escape of fast-moving particles from the surface of a liquid. Thus, the fast-moving particles of a liquid are constantly escaping from the liquid to form vapor. So the process of a liquid changing into vapor even below its boiling point is called evaporation. It can take place even at room temperature, though it is faster at higher temperatures. Whatever be the temperature at which evaporation takes place, the latent heat of vaporization must be supplied whenever a liquid changes to vapor. Occurs at surface, no bubbles formed. Occurs within liquid, bubbles appear. Let's understand factors affecting evaporation. Fast-moving particles in liquid escape and become vapor, while slow-moving particles in vapor stick back to the liquid. The rate of evaporation, drying up, is a balance between the rate of escape and the rate of return. Let's understand the temperature of water. The rate of evaporation. Let's understand the temperature of water. The rate of evaporation. Let's understand the temperature of water. The rate of evaporation. Let's understand the temperature of water.